Okay, let me start with a couple of announcements. Today is a makeup lecture. If you're, I'm not sure if this is being live webcasted, but if not, it'll be encoded and put on the web later on today. There's a homework due on Friday, and there's also midterm number 1 that's on Wednesday, October 22nd. As we get closer to that date, I'll tell you what material you're responsible for that midterm. Generally speaking, my policy is to only test you on the stuff that you've actually handed in your homework and received the solution for that homework. So it'll definitely include the stuff that's in Friday's homework, maybe a little bit more beyond that. Just another announcement. This is a note to Dan. Dan, I think it's a good idea to go ahead and put up the solutions to the problem set so far on the web for people who can download it, because I think I've received a large number of comments from you that you just find that to be more convenient, so let's just do that, especially with the errata and things getting corrected. So it's just with the latest version of it. Let's put it that way. And if you can go backtrack and do the, start from homework 1 essentially, that would be great. That's really all the announcements I have. Any questions or comments? Okay, very good. So what we talked about in last time's lecture was a variety of realizations and implementations of IIR filters that have rational transfer function. In particular, we talked about direct form 1, direct form 2, then parallel, then cascade. I'd like to wrap up that discussion by talking about transposition theorem, and then move on to FIR filters and how one goes about realizing FIR filters, and then move on along the same line, talk about linear phase FIR filters, and then after that, it turns out there's 4 kinds of linear phase. First I'll explain what the linear phase concept means, then I'll talk about 4 kinds of FIR filters that can easily achieve linear phase, and then we'll talk about IIR filters and the fact that how much more difficult it is to design linear phase IIR filters. And then we'll dive into designing FIR and IIR filters. So far we've talked about realization of them. We assumed that somehow, somewhere, the coefficients of these difference equations and the coefficients of the impulse responses are given to you, and you're just trying to come up with structures that realize them. Then the next topic after that is how to design these things. Where do these coefficients come from? If you have a set of specs, how do you ensure that you can come up with a filter that satisfies those specs? Okay. So let me start with today's topic, which is transposition theorem. And it's actually pretty straightforward. It refers to flow graphs, and what it says is that if you reverse the role of input and output, just label input as output and output as input, and if you also reverse the direction of all the arrows in your flow graph, you get the same system back. Okay, that's all that it says. So it says, let me write that down. So if you change the order of input / output, and then also change the direction of the flow graph, then you get the same system. That's what transposition theorem tells you. Okay. What we mean is that the same input-output relationship. Okay. So here we go. We start with x of n. Let me start with an example. As you remember, last time we talked about this second order generic terms that describe, that are in direct form too, and that could, for example, be a basic building structure for cascade or for parallel type system. But let's just repeat. It was called H sub k of z. I don't know if you remember that or not, but let's just write that down. Remember we had this H sub k of z, which looked like 1 plus beta 1k z to the inverse plus beta 2k z to the minus 2 over 1 minus alpha 1k z inverse minus alpha 2k z to the power of minus 2. And so let's draw that basic architecture that we came up with for this filter. And it had two delay elements in the middle, because it's a direct form too. The numerator and the denominator are sharing the same delay element. And it had arrows going up and down in the following way. And the coefficients then were alpha 1k here, beta 1k here, beta 2k here, and alpha 2k here. Okay. And out comes y of n. Okay. So what transposition theorem is telling you is that if I just go here and cross out y of n, make it x of n, and cross out x of n and make it y of n, and reverse the direction of the arrows, so it goes down like that. This is going up, and I could go down, going that way, go that way. And if I do that, and if I redraw the whole thing, then what do I get? I get a new system. And so let's redraw that. So it'll be y of n sticking out here, receiving an arrow that way. Let's draw the basic skeleton of the system. So, I forgot to make the reversed arrows up here. So this would be up, and this would be up. So they have two delay elements going up now, the inverses. The red arrows repeat here. These go down. These go down. And these go towards this node. This one goes that way. And that's about it. Now we can put the same elements as we had here. Beta 1k, beta 2k, alpha 2k, and alpha 1k. Okay. And here, instead of the arrow going that way, it's going this way. So it's x of n going that way. So now I get a new system. And this is the input now. And this is the output. And what I claim is that this system is going to have the same transfer function as this one, which was the original system. Okay. And as an illustration of this, let me just go through the formal derivation of it and prove to you that these two are exactly, not more or less, but they're exactly the same system. Again, this doesn't prove the transposition theorem in the most general way, but it gives you a plausibility argument that it could be true. So what I'm going to do is I'm going to name, in order to, how do I derive the input-output relationship here? So what I'm trying to come up with is y of z over x of z for this system here. And what I'm going to do is I'm going to name this node here r of n. Okay, question.
Are the arrows on your beta terms drawn right?
Actually, alpha is going that way, and beta 2k, no, it was going that way, so I'm drawing it that way. Let me hold on a sec. Okay, so it was this way. It should have been, this is wrong here. And it has to be red going that way. Is that right? Okay, thank you. and then here, so it has to be going that way. Okay, did that fix it? Thank you. Okay, so what we want to come up with is x of z over y of z, and the way we're going to do that is we're going to name this node here r of n, and then write down the loop equations that relates r of n, that's intermediate quantity, to x and y. So the purpose is at the end to come up with y of z over x of z. Okay. So what can we, now that we know this point is r of n, what can we say, what equation or what describes what the value of r of n is? Well, r of n is a node that is receiving input from here, here, and here. So r of n is really the sum of three things, okay? Well, let's write down what it is at this point. It's alpha 1k times this signal. Now, what is this signal? Well, this signal takes on, it seems like it's taking on its value from here and passes it to this guy and that guy. So what is, if it receives the signal from this point, what is the value of this point? Well, this point, again, seems to be receiving a signal from here and spitting it out that way and that way. So this point is y of n, because this point is y of n. And therefore, by this point is also y of n. This node is also y of n. So you get r of n is equal to alpha 1k times y of n plus, so that was just this branch, plus beta 1k times this node. But what is this point? Well, this node is the same as this node because it's receiving its value from up there and passing it along this way and that way. And what's this node? Well, this node is receiving its value from x of n and passing it this way and that way. So this node is just x of n, and this node is x of n. They're both x of n. So beta 1k times x of n plus this branch. Well, this is z inverse. So it's whatever signal it is, but delayed by 1. Well, whatever signal you have here, but just delayed by 1, is the contribution from this branch to r of n. Now, what's this point? Well, if this is y of n, this point seems that it's the sum of two things, alpha 2k times y of n plus beta 2k times x of n. So this will be alpha 2k times y of n plus beta 2k times x of n. So this is plus alpha 2k, and now this is this point, but now we have to delay that by 1 unit. So replace all the n's with n minus 1. So it will be alpha 2k times y of n minus 1 plus beta 2k times x of n minus 1. Okay? So that the sum of these four terms describes what r of n is. And the only reason I came up with this intermediate point is to help me relate y of n to x of n. And now, so we wrote down the expression of this being the sum of this guy, and that guy. Now, how can we write down the expression relating y to x? Well, let's write down y of n. So y of n here is this point, which is the same value as y of n here, right? This thing spitting out is y of n. This is coming down is y of n. This is coming down is y of n. So this point here is itself y of n. Okay. Now what can we say about y of n? Well, there's a branch feeding in from this way, x of n, and then there's a delayed element of r of n. So y of n is nothing but x of n plus r of n minus 1. So these are the two equations we're going to use. We're going to combine these two things now to relate y of n to x of n. And so the way we do it is we replace this r of n minus 1 with this equation here. So what we get is y of n is equal to x of n plus, now r of n minus 1 is this right-hand side here, but with all the n's replaced with n minus 1. So it would be alpha 1k, y of n minus 1, plus beta 1k, x of n minus 1, plus alpha 2k, y of n minus 2, plus beta 2k, x of n minus 2. So this is the expression now purely relating y of n to x of n. And now if you take the z transform of both sides of this equation, what you end up getting is the following. So you get y of z is equal to x of z plus z inverse alpha 1k y of z plus z inverse beta 1k x of z plus z to the minus 2 alpha 2k y of z plus beta 2k z to the power of minus 2 x of z. And then you can collect the y of z terms and x of z terms all in one side, and what you get is y of z over x of z is given by 1 plus beta 1k z inverse plus beta 2k z to the minus 2, 1 minus alpha 1k z inverse minus alpha 2k z to the minus 2, which is, bingo, it's the same expression as we had before as hk, as h sub k of z, which is the same thing as what we started off with before. So it didn't matter. So we started off with h sub k of z, and we drew the flow diagram for it. And then we changed the input to output, like it's shown here, reversed all the arrows, got a new flow graph, and came up with a system equation for that, and found out that after doing that, the system equation sort of remains the same. We'll do that also when we're dealing with FFTs. We'll also do the same thing where we change the input and output and the direction of the arrows. It's a cute little theorem, and it tells you that more than one second-order system can satisfy this input-output relationship. So that's not this direct form 2, if you will, is not the only way of implementing the second-order system. Okay. So other than that, I don't really have much to say about this transposition theorem. You can apply it. It doesn't just apply to this kind of a filter. You can apply it to any of the other structures that we had come up with. And if you do that, then you can see that the transfer function sort of remains the same. Question? Yeah.
Is there any intuition to why the theorem holds?
There is a formal proof to it, but the intuition, I can't think of a one-line sort of an intuition, other than the fact that, yeah, no, I can't say that, yeah. You're not just changing the direction of the arrows. You are also changing input and output. So I think the two of them, in my mind, the two of them have to go together for this thing to hold true. Any other questions or comments? Okay, so what I'd like to do is just move on. So far we've talked about IIR filters. So we've talked about realization of filters. We've talked about IIR filters and with rational transfer function. And now I'm going to start talking about FIR filters. In particular, just to remind you, for IIR filters, we talked about direct form 1, direct form 2, and then cascade and parallel. And I'm going to move on and talk about FIR, realization of FIR filters. What would be the structures that we use to implement those? Now, FIR filters per se, let's start off with asking this question: do they have a rational transfer function? What's the transfer function of FIR filter? What form does it take? If I have an h of n that has finitely many values, it has, let's say, n taps or n plus 1 taps or something like that. What's the transfer function for that? Well, h of z is just summation from n equals k equals 0 to capital N of h of k z to the minus k. So that'll be the transfer function of a FIR filter. Now, is that a rational transfer function? Rational transfer function was ratio of a polynomial of another polynomial. Yeah, this is a polynomial in Z inverse, and the denominator polynomial is just 1, which is a polynomial of degree 0 or something, right? So this is a rational transfer function, but the FIR filters don't have feedback, and we'll talk about that in just a second. They don't have a denominator at the bottom, okay? So difference equations are not the only way of implementing an FIR filter. What's other ways of implementing FIR filters? Anybody? Good old convolution. You got 5 taps or n taps, and you have even if you have a stream of infinite length of sequence of numbers coming in, you just flip the 5 numbers that are your FIR filter taps, multiply, add, shift, multiply, add, shift, multiply, add, shift, and the output just keeps spitting out. The IIR filters, you couldn't do good old convolution because there were infinitely many taps in it. And so difference equation was a way that sort of rescued you from that situation, specifically only if they had a rational transfer function where you could have a difference equation. For FIR filters, you can just do plain old convolution, but you can also come up with FIR filter structures that implement these things. So in this case, y of n is summation from k equals 0. So if I have a input x going into an FIR filter with n taps and output y coming up, then y is summation from k equals 0 to n of h of k, x of n minus k. Okay. And so you can write down the flow graph for this thing, and it's pretty straightforward. You start with x of n, okay? And the first thing that you do, well, let's expand this so that it's easy to understand. K is equal to 0, you get h of 0 times x of n, plus h of 1 times x of n minus 1, plus h of 2 times x of n minus 2, plus dot, 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 all the way plus h of capital N times x of n minus capital N. That's the expanded form of this summation. And so let's see if we can come up with a realization that implements this. So here's x of n. We're going to be multiplying it by h of 0 to get this term. And then we're going to be delaying it by 1 to generate at this node x of n minus 1, and then multiplying by h of 1, okay, and then delaying it by one more delay element, and then multiplying it by h of 2, all the way to the last piece, which is delayed for the last time, to generate x of n minus n, this is x of n minus n, and then multiply that by h of n. And before that, you were multiplying it by h of capital N minus 1. And now that you formed all these terms, you've got to be adding them. So here, add, and what comes out is just good old y of n. Okay? So this is the realization of this FIR filter. And is it direct form 1 or direct form 2? Anybody? It's the same. The difference between direct form 1 and direct form 2, remember before, was in direct form 1, the numerator and the denominator didn't share a delay element. In direct form 2, we collapsed them and they shared the same delay element. Here, there's no denominator. So it's a moot point. It's direct form 1 and direct form 2 both at the same time. There's nothing to be collapsed. So this is direct form 1 and 2 simultaneously. And now that we learned about transposition theorem, we can also transpose it and have the same system. So how would transposing this work? Well, call that x of n, reverse that arrow, and reverse all the other arrows. So it'll be arrow going this way. Each one is the inverse. And arrow going up, there will be h of 0, h of 1, h of 2, h of 3. Okay? And then arrow going that way. Okay? So, and out comes y of n. We're still opening. So this is another, the transposed version of this, and that just about implements the same system. Okay? Can we come up with a different, question? Yes, that is very true. Thank you. Thank you. Okay. So is there any, besides this direct form 1 and 2 and the transposition of it that implements this FIR filter, is there any, can we think of any other way of implementing this, realizing this FIR filter? Can we do cascade? Almost certainly. And what was the main idea behind cascade? Well, it was just you had a polynomial in the IIR case, the rational transfer function. You had a polynomial in the numerator and the denominator. You just factored it. You applied fundamental theorem of algebra. You found the roots. You could factor the numerator, which is the polynomial, and the denominator. All that's happened now is you don't have a denominator. Our transfer function is rational, but it only has a numerator. The denominator is 1, if you will. But we can still factor the numerator and come up with a cascade structure. So how would the cascade structure look like? Well, you start with your h of z, and what you can do is you can say it's a product, which we wrote already earlier, from k equals 0 to n, h of k, z to the minus k. We can write this as a product, a bunch of second-order terms, general second-order terms that sometimes become first-order. Remember, this is a polynomial of order n, and we are assuming h of k is real coefficients, and if it's real coefficients, the roots of it are either real or complex conjugate pair. If the complex conjugate pair, you get a second-order polynomial. If it's real, you get a first-order polynomial. But for simplicity, I'm just going to write a second-order polynomial and assume that the first-order polynomial is a special case of a second-order polynomial when the coefficient of the second-order term is 0. So here, write down as a bunch of product of second-order guys, b0k plus b1k z inverse plus b2k z to the minus 2. These are our second-order polynomials. And then sometimes if I wanted not talk about a complex conjugate zeros, I can just let b2k be equal to 0, and then it becomes a first order. And so how many of these would I have? Well, this is a nth order polynomial, so I can just say k ranging from 1 to n. Okay, and how would each one of these guys look like? Well, it's not all that difficult. You start with x of n and implement one of these guys. And how do you implement one of these guys? Well, one of these guys is the same as this guy, except without the denominator, right? Without the alphas. So these two branches will sort of go away, okay? So, I'm sorry, without the alpha, so these two branches will go away. That's what I meant to say. If alpha 1k and alpha 2k is equal to 0, the denominator becomes 1. We only have the numerator, and so these two branches go away, and we're left with this structure here. So if I were to copy that there, it'll be something like this. Okay, 2 delays coming down, and it'll be B01 this way, B11 this way, B21 this way, and arrows going up. So that'll be the first one. And then the second one would be another one of these guys with a slightly different coefficient, 2 delay elements. But now we'll have B02, B12, and then B22. So now here k was equal to 1, here k is equal to 2. And then you keep doing that, and then the last piece is another one of these guys with a different set of coefficients. Okay, so two more delay elements here, and B2M and B1M and B0M. Not M, sorry, N. Okay, and out comes the answer. So that'll be the cascade implementation of FIR filters. I'll talk about quantization effects later on when we talk about designing these things. And what becomes clear is that the cascade, so there's two kinds of quantization going on, okay? So this is a little preview of what's coming on in the future. Once you design a filter, you've come up with real numbers that signify these coefficients. When you want to actually implement it, a real number has a decimal point with infinitely many digits coming after that. No computation system has infinitely many digits. You could have fixed point arithmetic, you could have floating point arithmetic, but they all have finite precision. So in real life, when you want to try to implement this, there's the quantization of the coefficients. If you're doing 8-bit arithmetic, each one of these guys are quantized to 8 bits. That's all there is to it. So there's errors introduced because of that. And then furthermore, there's errors introduced in that if you think about having registers that adding up these numbers, your registers have finite length. So when you multiply an 8-bit number by another 8-bit number, you get 16 bits. And then if you multiply that 16-bit number by another 8-bit number, you get 24. You can't have your registers that grow in length arbitrarily. You have to have some kind of a truncation. It's called, finite word length effects, or finite word length arithmetic, whatever you want to call it. And so that's called round-off errors, right? So besides the fact that the coefficients are quantized, when you do these additions, multiplications, and the numbers propagating from here to here, etc., there's round-off effects going on. And one of the questions that was asked is, why are we discussing all these different structures? And it turns out, we'll cover this in a bit more detail later on, the cascade structure is less sensitive to these quantization effects of both the coefficients and also the round-off effects. Okay. At the end of the day, when these get quantized, and then when you introduce round-off effects, the implemented system implements a slightly different h of z than what you had originally had in mind because of these problems. And what I'm trying to say is that it has been shown with the fixed size arithmetic that these effects are the least pronounced when you have cascade structures. The poles move the least. Whereas in direct form, if you have an nth order system and you should build a gigantic direct form 1, the locations of the zeros move a lot more in that sort of a thing, but in that direct form 1, 2 type structure than they would in the cascade. So in some sense, the cascade structure is structure of choice if you worry about finite word length effects. And again, we will talk about that after I talk about design of filters. But I would like to take a show of hands and ask how many people ever had to worry about finite word length effects in anything they ever designed or built. Okay, just a couple of people. And was it implemented in a CPU or an ASIC or a TSP chip? Fun? FPGA. And what were you building, just out of curiosity? Filter on a? Okay. Okay. Very good. And how about, there was one other hand? FPGA. And what application was it? Uh-huh. Okay. So at the end of the day, even though, we all read in the paper just less than 5 days ago, AMD is coming out with a 64-bit CPU, right, just to beat Intel. And 64 bits is a lot of bits. And we'll talk about that later on. It's in floating point sort of arithmetic, so it's a lot of bits. And the trend is in that way. The finite word length effects are still important to study because, on your cell phone, we're not carrying an Athlon with 64 bits. That's just not a portable device. And on your cell phone, probably everything implemented in 8 bits or at most 16 bits arithmetic. So it's still very important to worry about the effects of it, because once you quantize these things and you do the round-off effect, the filter you wanted to have implemented, even though you designed it properly and under perfect implementation conditions, it's the filter that you designed, it would work. In reality, when you quantize things and do all these things, it's a different, you've implemented a different filter. And if that different filter doesn't satisfy the specs that you wanted, it doesn't reject the noise that you wanted it to reject, or it doesn't do the thing you wanted it to do, you haven't really accomplished anything. So finite world length effect is what real DSP engineers in industry spend a lot of time to worry about. Needless to say, everybody's desire, your managers, your boss's managers, and everybody's bosses, they all want to implement it in as few bits of arithmetic as it can possibly be done, because the larger these registers are, the more complicated your hardware becomes, the more power it chews up, the heavier it becomes, the harder it becomes. You know, it won't be the light portable thing that you want it to have. Okay? So we'll talk about some of these issues after we talked about filter design. But what I'd like to change gears is now is talk about what's called linear phase filtering, which I think the book also talks about in this chapter, but I might go a little bit deeper than what the book sort of covers. And I relate then linear phase filtering to FR filtering. So let me first start by defining what I mean by linear filter, and then motivate why we want to study linear phase filtering. So let's just do that. Okay. So by filtering, I really mean LTI filtering. I'm not using LTI and filtering in an interchangeable way. So recall from, I don't know, lecture number 1 or number 2 or something like that, one of the things that we learned about LTI systems was that if you input to it some sort of an exponential, e to the j omega n, so an LTI filter, then what comes out of it is the same exponential times some other number, which we called h of omega, which we discovered is the DTFT of h of n, which we also call the frequency response of this filter at omega. Okay, so you put in an exponential of frequency omega, and what comes out is the same exponential, and how much it got scaled is a function of omega. So if you put in e to the j 5n, sinusoid of frequency 5 or something, e to the j 5n comes out, and depending upon what h of 5 is, the magnitude of that sinusoid either got bigger or smaller, or it just got scaled by h of 5. Okay? And what do I really mean by linear phase? Well, if I now talk about a slightly more general form of this, for example, x of n, going into an LTI filter with h of n, and out comes y of n, then I can write down the relationship between the Fourier transform of these two guys. Y of omega is x of omega times h of omega. That's convolution property corresponds to, in time domain, corresponds to multiplication in the frequency domain. You all know that. And now I can write the magnitude and phase of this thing. In particular, magnitude of y of omega is magnitude of h of omega times magnitude of x of omega, and the phase of y of omega is equal to the phase of h of omega, what? Plus phase of x of omega. Magnitudes get multiplied, phases get added. And this symbol here denotes phase. This all comes in properties of complex numbers and how you do things. Okay? So, in a nutshell, what is the definition of a linear phase filter, LTI, or what's the definition of a linear phase LTI system? All it means is that this function, angle of h of omega, is linear as a function of omega. The name is on it. It's not quadratic, it's not cubic, it's not funny, it's not anything bad, it's just linear. So let me write that down. So the definition that we have here is that a linear phase LTI system or a filter, we call this the same thing, the angle of h of omega is linear in omega. That means it is of the form alpha times omega plus beta. That's what we mean for something being linear. So if I were to plot it as a function of omega, here's h of omega, I get just a line. That's all there is to it. Where when omega is equal to 0, it intersects here at beta. And we'll just talk about why linear phase systems are important in just a second. But so what is an example of a linear phase system? Consider just a pure delay. Okay, so h of n is equal to delta of n minus n sub d. Okay. What can we say about h of omega here? Well, magnitude of h of omega is 1, and the angle of h of omega is what? You can compute the Fourier transform of that. What's the Fourier transform of this? That's the discrete time Fourier transform. E to the minus j omega n d, right? It's just a delay element. So the phase of it is minus omega n sub d, right? You can, by just writing down the expression for this, right? Because the discrete time Fourier transform is e to the minus j omega n d. So if I have, that's really what I mean by phase. Is, a complex number consists of a magnitude times e to the j phase. So this is what the phase is. And if I were to plot then, if I were to plot angle of h of omega, okay, is that clear, the definition of phase to everyone, or do you want me to write it down? No? Everyone knows? Okay. So if I were to plot this angle of h of omega as a function of omega, what do I get? It's minus nd. So it's a straight, at omega equals 0, I get 0, and then it goes down. And somehow it reaches 2 pi, but phase sort of wraps around. So we could have phases of like 2.5 pi, 3 pi, 4 pi, 6 pi, a million pi, but I don't want to. But in reality, the phase of something that's at pi over 2 is the same as pi over 2 plus 2 pi plus 4 pi plus 2k pi. So let's just write down the unwrapped phase rather than wrapped phase. And unwrapped, all it means is that it comes back when 0 and 2 pi are the same. Comes back like that. Okay? And what it says is that the slope of this line is minus nd, n sub d. Okay? So what does that mean? That means that it's there at the system. So if I have just a pure delay system, is that a linear phase? Yeah, absolutely. It's got lines that is phase as a function of omega is a line. And the fact that it's not really a straight line going down all the way to infinity because I chose to unwrap it and just show it between 0 and 2 pi, it's linear. And so it's sure enough pure delay is a linear phase system. And I can also talk about a new notion which is called group delay. Okay, so I'm going to define group delay of a filter, and I put a little triangle here. This is the definition, is minus the derivative of the phase of h of omega with respect to omega. Okay? So if that's my general definition, then plugging it into here, into this thing, so if angle of h of omega is minus omega n sub d, that means that the group delay for it is equal to minus d omega minus omega n sub d, omega n sub d, and the derivative of this with respect to that is just n sub d. So the group delay for this filter up here is just n sub d. And does that make sense? Yeah. This is a filter that just delays everything by n sub d, and therefore it makes sense for its group delay to be n sub d. Okay? So this filter is not only linear phase, but it's also at the group delay of n sub d. But more important than that, the fact that this group delay here is independent of omega. So this n sub d is independent of omega. What does that mean? Well, what that means is that for this delay system, it doesn't matter you put in sinusoid of what frequency. It doesn't matter what frequency sinusoid you put into it. It always delays all sinusoids of all different frequencies by n sub d. Okay? So the amount to the fact that here in this example the group delay is independent of omega, intuitively what that means is that it delays all different frequencies the same amount. So let's write that down. Okay? So this is independent of omega, which means that this system delays all sinusoids of different frequencies by the same amount, okay, which is n sub d. So you put in a sinusoid of 10 hertz, it delays it by n sub d. A million hertz, the same amount. And what does that imply? Well, let's draw a little picture here. So suppose, could you zoom out so the entire picture thing is in it? Thank you. So suppose that I have a group delay here of n sub d, an LTI system. Let's say the delay, the same thing as we just had, the pure delay system. That means if I input to it, let's say, sum of different sinusoids, cosine omega naught n plus cosine omega 1n plus cosine omega 2n, where these are all different. So at the input, let's say cosine, so here's cosine omega naught n, pictorially. So that gets, it starts at time 0, and it gets delayed by time nd. So it does what comes out. This is the input, and this column is the output. Okay, and cosine omega 1n, let's say starts at time 0, and it does this. It's a slightly higher frequency, and I'm terrible at drawing pure cosines, but assume this is a pure cosine. And how does this come out? Well, it just gets delayed. So if at time 0 it was at a peak, so now at time n sub d it's at the peak. Okay? And so if I had the input, the sum of this and this as my input, the phase relationship between these two was fixed as the input. They have the same phase relationship when they come out at the output. Why? Because this system delayed both of them by n sub d. If they had this funny phase relationship at time 0 at the input, because all that happened, both of them got delayed by the same amount, they have the same phase relationship at the output. So if the sum of this signal plus this signal, and again, I'm a terrible artist, but look like something garbage looking like that, the sum of this plus that is the same thing, but same garbage looking thing, but identically, but just shifted. That means the waveform didn't get distorted as it went through the system. Why? Because the phase relationship between these two got preserved because both of them got delayed by the same amount. Okay? Because the amount that this system delays things is independent of the frequencies. And now I drew a sum of 2 frequencies, but you can extend it to sum of 1,000,000 frequencies. If I had 1,000,000 of these cosine terms, and a sum of 1,000,000 frequencies is typically the way you express any arbitrary waveform anyway. That's what Fourier series expansion is all about, but I only drew that just for the sake of example. What that means is that the linear phase system, is a system with a constant group delay, does not distort the input waveform. Okay? So the conclusion here, so this thing looks the same, if you will, but the conclusion is that observation is that if I have linear phase, which means this, if I have linear phase, when I take the derivative of linear phase, I get a constant group delay. So linear phase and constant group delay is the same thing, which is the same thing as group delay being constant. Then the conclusion I want to get is that no distortion is introduced in the output. That means the shape of the waveform sort of comes out intact. Maybe it got scaled a little bit if this guy has a scaling thing, magnitude of it, like if magnitude of Fourier transform wasn't 1. In our example, we had such a simple system. We had just a pure delay, but suppose there was a scale factor like multiplied by 100. So maybe this thing would be 100 times bigger than that, but the shape of it will be the same. So the bottom line is the linear phase filters or constant group delay filters are good in situations where you want to not introduce any distortion. And where is one example where that's an important thing? Well, in image processing. Okay? So as it turns out, in image processing, images are made of a lot of edges. In fact, that's the way humans perceive images most of the time. So let's just draw a one-dimensional depiction of an edge. Edge means, the intensity is like low, and then boom, a sharp change, and it becomes some other value. And and what you want to do is, in image processing, when you process an image, you don't want the edges to get blurred. You want the edges to be preserved. And so we pass this edge type signal into a LTI system, and I'm going to argue that if it's linear phase, what comes out is also a nice looking edge. And why is that? Well, I can decompose an edge into a sum of a bunch of sinusoids, right? Remember the Gibbs phenomena, where we had at the beginning, you had a box and you keep adding more sinusoids, and the thing approximates the box more. So an edge is nothing but a sum of a bunch of frequencies. But the frequencies, a lot of them could be very, very, very high frequencies, and some of them are very low frequencies. So it turns out if I add these sinusoids at the right phase with each other at the input, I can reconstruct an edge pretty well. We talked about that already, right? And so if I pass it through a linear phase system where the group delay is constant, where each of these sinusoids that constituted this thing got delayed by the same amount, what comes out they have the same phase relationship at the output than they have at the input, because each of them got delayed by the same amount. So if they had a certain phase relationship with respect to each other at the input, because my LTI system was linear phase, and it just purely delayed each of them independent of the frequencies, they have the same phase relationship at the output. So when I add them up, I get the same edges I had before. Okay? So what I'm trying to say is that in image processing applications, as an example, it helps to have linear phase LTI systems in order to preserve edges. And preserving edges is a good thing, because you don't want your images to come out all blurred out and washed out and not sharp after you're all done with processing your signal. Okay? So how can I now be a little bit more sort of formal about these linear phase systems? Okay? And what can I show about them, or what can I say about them? Well, consider a really narrowband signal. And what's the meaning of a narrowband signal? Well, a narrowband signal is one, let's say, whose Fourier transform, discrete time Fourier transform x of omega, it's centered, let's say, around omega naught, but its bandwidth is much, much smaller compared to omega naught. Okay? So its bandwidth is like delta of omega. What's an example of a situation in real life that you see a narrowband signal like this? Yeah, communications. When you modulate the signal, let's say a voice signal, all the way to, 88 megahertz to transmit it over the FM channel or whatever, then the bandwidth of the signal is still a voice thing, maybe 10 kilohertz, 20 kilohertz, or something like that. But the frequency is meant for that omega naught is many, many megahertz. So by narrowband, I mean delta of omega is much, much smaller than omega naught. Okay. So for example, if you're listening to KQED radio, then omega naught is 88.5 megahertz. And omega naught, and delta of omega is what? What's the spacing between the FM channels? Let's say 200 kilohertz or so. So it'll be 0.2 megahertz. So this number is much smaller than that. Okay. So what would be an example? How could I write this thing? Well, I can write an expression for x of n as it's s of n, which is the signal that carries the information, times cosine omega naught n. So the cosine omega naught n is just modulating it to this high frequency. Okay. By the way, one of the trends in radio signal processing is previously when you design radios, you receive the signal, you have a filter, you receive the signal. First you demodulate it, you bring to baseband, and then you A to D it, you sample it A to D. And now one of the trends is the A to D technology has improved so much that you can even sample this at twice the 88.5 megahertz at 170 megahertz, for example. So you don't even do any analog processing. The very, very first step is D to A, A to D, and then beating back it down here is also done digitally. Everything is done completely digitally. Anyway, that's besides the point. But here's the expression for this signal. X of n is S of n, which is the information carrying part times cosine omega naught n. And suppose that we pass this signal X of n through some filter H of omega, where the magnitude of H of omega is 1, so we don't do any kind of a scaling. But the phase of it is linear at omega equals omega naught. Okay? So let's write this down. So you pass X of n through some LTI filter, H of omega, such that magnitude of H of omega is 1, but you can approximate the angle of H of omega at omega equals omega naught with a linear phase, okay? With a linear term like this, you can say that angle of H of omega in the vicinity of omega equals omega naught. It could do all kinds of weird things, nonlinear, up-down, quadratic, cubic, all kinds of funny things here, but our signal is very narrow band, so we don't really care what it does here. But in this small region, we can say that it's linear, okay? And what it's linear to, we can approximate it with like a constant, phi, minus omega n sub d. Okay? As you know, over a small region, if I have this comes from the following fact, is that if I have well, I'm just going to draw it here. If I have angle of H of omega, even though it can do all kinds of funny things here, all that I'm saying is that over this little range around omega naught, it's so tiny that even if it's doing weird things, I can linearize it around it and make a linear approximation here. Yeah, question?
Well, what I was going to ask was, for any linear response, right, the slope doesn't need to be omega, but I did answer that myself, so you don't need to.
Okay, all right. So whatever this angle of H of omega is doing all kinds of weird things, but you can always, if you're looking at a small region, you can always linearize any function. In fact, you can use Taylor series expansion to come up with a constant approximation, then a linear term, then a quadratic term, a third order term, fourth order term. And all I'm saying is, in this small omega naught, in this delta of omega region, around omega, centered around omega naught, that's just approximated with the linear phase, okay? Which means that all I'm saying is that minus the derivative of the angle at omega equals omega naught is just n sub b. That's all it is. Okay? So if we pass this signal, this narrowband signal, which is of this form, through a filter which is of this form, what we can show is that the output, and I'm not going to show it, I think it's one of the homework assignments, not for this week, but the week after, we can show that the output y of n is just going to be simply the delayed version of this thing. It will be s of n minus nd times cosine of omega naught n minus omega naught n sub d minus phi. Okay? So all this thing it really did is, because it delayed, if you replace n with n minus nd, which is the delay element, and then a minus phi because this is a constant term here. Okay? So generally speaking, for the conclusion I want to get out of this whole discussion is that can you make half of this show up, please? So the can you make half of this previous page? Just lower the camera. Oh, great, thank you. So the conclusion I want to reach is that for a narrowband signal, if I pass it through a filter whose group delay is constant at the center frequency of the narrowband, then you can have a simple sort of a processing step where each element gets delayed by this amount. Okay, so let me write that down. So for a narrowband signal, delay is proportional to the following. Group delay is proportional to minus dB omega of h of omega, where omega is evaluated at omega equals omega naught. So for a narrowband signal centered, I have to add this, centered at omega naught, then the delay is proportional to this amount. So it doesn't matter if the filter h of omega was not truly a linear phase filter for all frequencies, because the signal itself is only non-zero centered around omega naught. You can do this linearization thing, and you can compute the amount of delay by using this little expression. You can take the derivative of it at omega equals omega naught, approximate it, and that tells you how much delay you have. So once again, I emphasize this, where omega naught is the center frequency of the narrowband signal. Okay? So hold on a second. So if I now consider a sum of three sinusoids one more time, x of n is a times cosine omega naught n plus b times cosine omega 1 n plus c times cosine omega 2 n. Okay? And we pass this x of n through some filter h of omega, and out comes y of n. And suppose as a function of omega, h of omega at three different frequencies does three different things. At omega naught, it can be approximated with a linear line with slope of nd naught. At here, it has a slope that can be approximated with nd1, and at here, it has even a steeper slope that can be approximated at nd2. Then, when this thing when this thing is an input to this, when the signal is input to this filter, what comes out of it, again, can you make half of this page, the top page show? what comes out of it really is this thing delayed. So a cosine omega naught n goes in, and what comes out is a cosine omega naught n minus omega naught n d naught. And a cosine omega 1n comes out with a different amount of delay. So here I'm assuming that phi is equal to 0. Okay, so it will be b times cosine omega 1n minus omega 1 n d1. And I'm sorry, this is b going in. And then c times cosine omega 2n coming out c cosine omega 2n minus omega 2 n d2. So they all got delayed by the same amount, and so the output that comes out y of n is just the sum of these things. It's a cosine omega naught n minus omega naught n d naught plus b times cosine omega 1 n minus omega 1 n d1 plus c times cosine omega 2 n minus omega 2 n d2. And so if n, so what I'm trying to say is that if n d naught and n d1 and n d2, the three delay elements, they're not the same, and I had this sort of a relationship between, this is the cosine omega naught n, this is cosine omega 1 n. If they had this sort of a relationship and this guy got delayed, let's say this is time 0 and this is time 0. And if they got delayed by different amounts, when I add them up, the waveform looks sort of distorted. Okay? So the conclusion I want to get is that it's more or less the same as what I said earlier. If n d naught is equal to n d1 is equal to n d2, I get no distortion. The phase relationship between these things remains the same. But otherwise, I get sort of a distorted signal coming out. Okay? Now, there was a question.
I was wondering if there's a relationship between this linear phase and time invariant.
No. You could have time invariance and not linear phase at all. The linear phase, strictly speaking, refers, if you don't have time invariance, you don't have an LTI filter, you don't have an H of n, you don't have an H of omega to talk about all of these things. So a subset of LTI systems have linear phase. Okay. Okay. So I think I'm going to stop here because this is a good point. You got a sort of an intuitive idea of what linear phase means. And what I'm going to talk about next time is sort of the 4 different kinds of linear phase filters and how can we achieve, now that it's such a good property and it makes things not to be distorted, how can we achieve it? And it turns out with FIR filters, it's so easy to achieve linear phase. All you do is you impose some symmetry conditions on your H of n. And it turns out with IR filters, it's so difficult to achieve linear phase. And so those are the kinds of things we'll talk about on Wednesday.
So we are assuming it's a narrow band, right? So one